Yan, Kuya Dre. Patotoo.
Unique really factor. And then swap.
So just in case. But
Thanks. Sit here for a second.
yeah, sure, absolutely. You need that flip thingy? You need the flip thingy?
Yes.
That's a sensible watch face.
I don't know.
Bigger than mine, yeah?
No, I think it's smaller.
It's definitely not smaller.
Okay, then
But
maybe
do you know what the
I can change the watch face on my phone. It's
but the
connected.
thickness, the
The
diameter.
diameter. I don't know. I had to look it up.
Somebody's mic is on.
Is it mine?
I'm not sure.
Mine
The speaker for this morning is Isabel Colby from NITheCS on jet energy loss in the 00 era.
Thank you. Fantastic. So I think with Will's introduction yesterday on the QGP and why that's interesting, I won't like dwell on that too much, but I did want to sort of talk a little bit about how I think in the sort of my future direction of thinking will be very much in line with this sort of oxygen run, which is really exciting. So I put here an Atlas event display from last week. I don't know if you can see, but the date here is the 7th of July. So last week, the LHC ran oxygen for the first time. And I'll maybe say a little bit about why that's interesting in a bit. But okay, so no? Yes, okay. I think just to sort of say very quickly, the main sort of drive of this research is to have a look at jet energy loss. And the way to sort of explain this is that, okay, if you think about a proton-proton event, this is again an Atlas event display. The general way of thinking about this is that, okay, I see two calorimeter towers. These are, if you imagine, here comes the beam in here, and you have wrapped around it a detector. If you flatten this detector out, you see here a jet in this direction, a jet in that direction, or these are the same ones, this one and that one. And if you flatten this calorimeter out, you see two towers that are the same height, essentially. To Ethereus, this is the same height. I think this is causing Tian some pain that they're not. They, in fact, are not the same height. But okay, so Ethereus, this is the same height, because what we think is you produce these jets back to back and they have the same amount of energy. But if you put this in a heavy ion collision, so now this is also an event display, but now for lead. Okay, I've cheated, I've taken an ultra central event, but you see that each of these yellow lines is a track made by a particle. And what you see in the transverse plane is that, okay, I do see the one calorimeter tower coming out this way, but in a back-to-back region, the experimentalists have drawn to guide the eye where they have seen the jet, where a jet finding algorithm will see a jet there. But by eye, you can't see anything in the calorimeter tower. And the argument is that this jet has lost energy traveling through the plasma. And what we believe we can do is that if you can model this interaction with the plasma carefully enough, you can extract some information and learn something about the quark-gluon plasma. So that's the goal of this research in some sense. But in order to do this, you really need to have a careful, very careful modeling. And the problem is that the evolution of this plasma has several stages, each of which requires significant modeling. So there's a big problem in trying to understand the initial condition. What is the difference between a superposition of protons and neutrons versus like a lead nucleus, which is far more than the sum of just a superposition of protons and neutrons? Then there's some sort of evolution. Once you've collided these things, there has to be some evolution that brings you to equilibrium, because we want to use we believe that you have this like fluid, and if you want to describe that using thermodynamics, you need to thermalize in some way. You need to reach some equilibrium. That takes a while. We don't really understand how that happens. Okay, then there's the QGP evolution, and then hadronizers and so on. And the reason we are interested in the jets is because the jets are really produced in this first initial collision. The very hard partons are produced here, which means that as they travel through the plasma in all of stages of its evolution. So in principle, there should be an imprint of this evolution on these jets. On every stage of this evolution should have an imprint on the jet. Okay, but good. So we will try to model this and try to extract some information. Oh, I have the thing in my hand. Okay, so good. So that's the basic story. Now we calm down. Now I work on I try to approach this problem from two different sides. One is analytical and one is computational. The analytical one at this stage is, I almost just do it because it's like my favorite calculation. It was my master's calculation and I enjoyed it, and it's like a little bit nostalgic, and I've managed to come back to it. So on the next slide, you will see an archive number here, which is 10 years old. Okay, so initially how we did this was one of the problems that you run into, which Will's group also works on, is the question of small systems. And in the end, the point is just you calculate diagrams like this. And in order to do this, you have to make several simplifying approximations, one of which is that the system is large. But when you do this calculation carefully, you find that, and this was later on done by Will and Cole, you find that the result sort of blows away. If you try to say, okay, in the initial approximation, the system is large. If you relax this approximation so that you really only work with the necessary things for the model, you find that everything blows up, and it's really difficult to deal with. You get some serious problems. And the problem is just sort of notice that forget what this observable is for now, just you expect it to be less than 1. It's very difficult in this model to understand why it would ever be more than 1, but you see that the red line does become more than 1. And that's because there's some issue. And so what I have been trying to work on is trying to understand what the contributions are to this blow up. And so what a master student of mine has just worked on is, okay, so I apologize for these very ugly looking equations, but okay, all I want you to do is to see, okay, so in the initial calculation, there's some prefactor here, and you get this very nice, simple thing. Then in my master's calculation, again, you see here's the prefactor, but here's this all path length. You see this is all the same, but then you get some additional factor, which has this small system approximation. Okay, what we have done here, in fact, is not even the radiative energy loss calculation, it's just the broadening. So in the previous slide, you have a hard production, you scatter off the medium, and you radiate. I think we know the source of this problem, but it is. Will and I, even when I was in my master's student, we decided we weren't willing to do this calculation. It's just too much work. So I've done the easier version, which doesn't even have the radiation. It's just the broadening. It's just the scattering. And this is what you get. So you've gone from this like very nice simple thing to this mess. And again, here's this prefactor, right? You see this very nice prefactor that we had before. Here's even part of it, but already it's not even possible to get this nice squaring and just in the broadening. So, okay, so this is very preliminary results. I saw this 2 days ago for the first time. So we are still trying to see whether there's a way to make this look nicer. And then of course we will have to do the numerics. And I suspect that another origin of the problem here is that the integration bounds here are not carefully controlled. So we have to think about that a little bit more carefully. Good, so that's on the analytical side. It's almost just because it's a calculation I know, so good. Okay, but I have actually spent the vast majority of my sort of post-PhD time working on computational things. One of the problems, okay, so how do you model this jet in the plasma using sort of Monte Carlo methods? And we use this sort of Monte Carlo simulation software called Joule, jet evolution with energy loss. And okay, you don't have to read all the things. The point is just that you have a parton shower in which you start with some hard production, then you have some in-medium evolution of this hard production. It includes vacuum radiation. It also includes the medium modification of the splitting functions, of just the D-gap splitting functions, but then also it has these collisional terms and so on. Okay, good. And the point is just that, okay, you have this energy loss model. This is open source software, but one of the problems here is that when you download this, it comes with a model for the medium, which is a very simple model. You simply take 2 wood saxons for your nuclei, you overlap them, you get a density, or you get some density. You use an ideal gas law to give you a temperature, and then all you do at every step is you ask, you evolve your parton, you say, what's the temperature here? And then I take this temperature and I create from it a sort of a pseudo particle, which I do 2-to-2 scattering with. Okay, but if we want to start going to the oxygen era, where now your systems are smaller, there's more fluctuations, you really can't rely on these smooth temperature profiles. So what I wanted to do and only have recently managed to do is to implement a way to run Joule on a sophisticated hydrodynamic background. So good. What is this hydrodynamic background we use? This triectum. Again, I didn't write this. These are my collaborators. But what they have is a simulation software which really simulates all of those stages that I spoke about at the beginning of the evolution of this plasma. So there's an initial stage, there's a thermalization period, there's the hydrodynamic stage, then they also have hydronization and all of these sort of different phases. I don't really want to talk about it too much, except to say that it is very fast. You can run it on your laptop, and they have done a full Bayesian analysis across several experimental observables. I think like 2,000 data points or something. So there's no tuning that we can do here. There's no reasonable tuning that you should do. It's been the parameters have been fit to data in a very strong Bayesian way. So good. So that's just there. Okay, good. What can we do with this? So what I've done, myself and now also these other collaborators, is we've put together a way to put Joule on top of triectum, which took much longer than I thought it would. And maybe a similar problem to what Anoush had. You think it's going to be easy, and if we had known it would be so hard, maybe we wouldn't have done it. But in any case, we've done it sort of very carefully. And I think the most important thing for me is that if you have this simple model that Joule ships with, you have no transverse expansion of the medium. It only cools down. And that's problematic because we know that the medium is expanding very fast in the transverse direction. And so what we have managed to do is include this transverse expansion into the way that you get an effective density, by which I mean that if my parton is sort of traveling, but the medium is flowing against it, it will feel a stronger interaction versus when it travels with the medium. And that seems to be quite important. Okay, so good. So here's some simulations. Okay, what I have here for you is the same triectum profile, 3 of them, but I'm running 3 different Joule events on the same profile. And what you see from the triectum profile, the first thing to notice is that it's not a head-on collision. It's a slightly off-center collision. This is lead-lead. So you will see this almondish shape. You also see that it's quite lumpy. So the lumpiness is, again, is also important. Good. And then what you see is that this is the temperature scale. So you see that it cools down quite rapidly and it is expanding in the transverse direction. And then what the dots are Joule. What I've asked Joule to do is output every time it interacts with the medium and asks what's the temperature here or collides with the medium. Just tell me you did that and tell me what the momentum is of the parton. So larger, darker dots are high momentum partons, smaller, lighter dots are softer. And then reds are gluons, reddish ones are gluons, bluish ones are quarks. Okay, now let's look at this a little bit more carefully. So now that you know what you're looking at, see here, for instance, let's look at this one. So I have a production point here, and my partons travel, but you will see that it hits something in the medium that's flowing against it here. It really changes direction. And I think that, and it changes significantly, right? It's almost 45-degree change in direction, which I think is not easy to do in these like analytical calculations. And I think you wouldn't have noticed this if we hadn't done this, this kind of animation. The other thing is that one of the things we're after in this question about the energy loss in the medium is the path length dependence. There are these sort of hand wavy arguments that the energy loss goes like L squared. We've known for a long time that's probably not true, but one of the ways we try to extract this path length dependence is to say within a system like this, which is very elliptical, you'd imagine that a parton that travels in this direction loses more energy than a parton that travels in this direction. But in fact, even just in this picture, you can see that that's not true. Even just in this picture, you can already see that these guys are barely affected, whereas the ones that have gone in this direction, this guy is changing direction very much. And then what this points to is the idea that the fluctuations in the fragmentation of the jet are almost more important than the fluctuations in this medium. So, okay, I haven't really had time to sit and stare at these with much more detail, but I think that they are very, very sort of interesting, and it's nice to be able to see it. Okay, good. Let's talk about what you can do with this. So one of the things, so this is again, this observable that you expect to be less than 1, just to sort of say that there's some energy loss. And what we've done here is that we've run on, say, you run 1,000, I think we did 1,000 Joule events on each of 500 different triectum profiles, and then you get this solid line. But if you randomly choose some of these triectum profiles and you just run a bunch of Joule on them, then you get these thinner lines. And the point is just to say that if you had incorrectly chosen a different triectum profile, you could get up to 20% difference in your energy loss calculation, which is just to say that you really need the ensemble, you need the averages, even in central lead, where we usually argue that this is unimportant because the system is so large and everything gets washed out. Okay, so I always like to show this plot just because it took me forever to make, but then I also think it's quite spectacular just to show that this blue, the dark blue line, is the line we get by running this Joule on triectum, and we did not tune anything. 5 minutes, very good. And we tuned nothing. I just ran it, and it goes straight through the data points. And that's partly because, of course, triectum is already tuned to the data, but triectum is not tuned to high momentum data, only to low PT data. So I thought that this was quite spectacular. But we will have to go on. This is in lead. Now, oxygen, good. I just wanted to argue quickly why oxygen is interesting. So when we think about small systems, we often think about something like a proton-lead collision, but that is very uncontrolled experimentally to sort of select events that have a lot of particles in them. But here you have, okay, so the number of binary collisions, the number of participant nucleons. Maybe none of this is so important. All I wanted you to see is that the oxygen-oxygen collisions have about the same number of binary collisions as 70 to 90%, very peripheral lead-lead collision, and is pretty close to a high multiplicity proton-lead collision. So what we're trying to argue here is that the oxygen-oxygen collisions are much more controlled, much more easy to deal with, and they have the same, in principle, system size. So that's why we want to go there. What we can do here with this software now is really explore the effect of the initial condition. So, if you have this fluctuating underlying background, means you will have more hotspots, you will have steeper velocity gradients in some directions, and you have to deal with that problem. We can also now look carefully at the jet fragmentation, which you probably in principle could have done in vacuum, and you could have done this with the old Joule, but now you can really do it carefully to see which effect is the bigger problem. We'd also like to look at the path length dependence. So you can now do a real system scan. You can do oxygen to lead. You don't have to do a quote unquote system size scan by looking at peripheral lead, because the peripheral lead is not the same as a central lead. So this is going to be very fun to do. And then actually my initial motivation for doing this was to try to look for different observables. This observable I showed you that has to be less than 1 is poorly controlled in small systems, but we'll now be able to have a look at, and we have sort of developed some analysis software and so on to do all of that. So we will go into oxygen, and maybe I think I just have a quick animation. So this is the trajectum for lead, and here's the trajectum for oxygen. So you can really see that it's smaller, but very similar. So it is a bit colder, but it really has the same shape. It has the same sort of, basic properties. So you now really are doing a real system scan. You're not changing the shapes and stuff. Yeah. Okay, good. And so there are some other things you can quickly do with this. We don't have to just look at OO. We can also look at the way that if the medium is flowing transverse to your jet, does it shift out? You can look at that. You can also, because you have complete control with this interface, you can just make up your own hydrodynamic background, put in a brick if you want it, but play with the starting time of the energy loss. So you can do all of that, and I'm done. Sorry, I've gone completely over time now already. Yeah? Still a minute. Good. Okay, so the conclusions here are that, I do work on some analytical things, and those are fun to work on, but I have not managed to find many students to work on it. And the current student wants to ride up and leave, so we'll see. But we have this hydro plugin for Joule, so we can really start playing with all kinds of, you have any kind of idea about, is it this thing or that thing? You just write your own little temperature profile and run Joule on it, and it's kind of fun. It's kind of fun to see what these effects are. And we've done the proof of concept in lead, so everything works in lead, and we're just currently running on OO, which is why Kevin wasn't allowed to use the cluster yesterday. So, okay, cool. Thank you very much.
We have a few minutes for questions.
I have a question about the pre-equilibrium dynamic. Is that implemented in trajectum as well?
Yeah, so I forget now precisely what it is that they do, but they have some evolution that they've taken from this kinetic theory. But in fact, it turns out that maybe that's not so important. What I thought was more impressive is that one of their parameters is the starting time of the hydrodynamization. So the hydrodynamic starts, usually people set it at like 0.6 or something. They have that as a varying parameter within their Bayesian analysis, and which means that you have to find a way to do this so that it's not too sensitive to that. So their switching time from this non-equilibrium phase to the hydrodynamic phase is a parameter in the Bayesian analysis, and which they are not very sensitive to. So they've even showed that within their setup that goes from this kinetic theory into the hydro, they're not very sensitive to where you switch from one to the other, which you would expect. That sort of seems important, yeah. Whereas some of these models are, right? This, what is this one of Magda's? I forget now. It has Drina B. That's very sensitive to its starting time. In fact, they wrote a whole paper to say how it's really important to choose the starting time carefully. Theirs is very sensitive to when you turn the hydro on, but that doesn't seem very physical, yeah.
Let's thank you, Isabel, again.
Thank you very much.
Then follow us.
Yeah, you can come here. Yeah, I think so. Unless you want to talk there, I guess. I don't. Here's Anosha's thing. I will leave it here for you. Yes? Can I leave it here for Paolo? Oh, sorry. No. Where is it? Oh.
Let's over there. I'll see what you're not allowed.
Yes, sir.
Oh, okay.
On chaos complexity and Q. Please go ahead, Mark.
Okay, thank you, everybody, and especially thank you, Vishnu, for arranging this conference. So let me start talking. So I'll talk about chaos, complexity, and QFT. I'll try to give you a glimpse of my research, that what exactly that I did and what exactly that I'm doing now. And if there is any room for collaboration, I'll just present myself to you guys and let you decide. Okay, so what did I do in the past? So most of my work revolves around ADS-CFT. So ADS-CFT, I'm not getting into any kind of technical detail, but ADS-CFT, as you know, is a conjectured correspondence between, it is called ADS-CFT, strong-weak duality. It is a conjectured correspondence between a strongly coupled field theory and a weakly coupled string theory, or a theory which involves gravity. So string, gravity on one side, and QFT on one side. As you know, most of the problems that we encounter in real life could be formed in the language of QFT. QFT is what governs the world we see around us. So what happens is that what is the phases of strongly coupled QFT? For example, here I have given you a plot of this famous UCD phase diagram, like quark, gluon, plasma. There are various phases, etc. And it's an open question that how to understand those things. And there are similar open questions in the field of superconductivity, like superconductors, and various other quantum matter phenomena like quench, etc., which involves very strongly coupled QFTs. So one direction of my research was to understand these phenomenon in strongly coupled QFTs using a weakly coupled gravity dual. That is what means that this ADS space looks like this kind of strange cylinder where these cross sections are hyperbolic, and then you put those hyperbolic spaces in a cylinder. And you consider black hole and other gravity solutions in this cylinder to understand QFT phenomenon. So my previous work, what I did is that I worked in ADS-CMT, that is where we use this ADS-CFT correspondence to study condensed matter theory. And what kind of condensed matter system we looked at? We looked at holographic superconductor, superfluid, we looked at quantum quench, these and few other similar things and various other properties like response, etc., of those theories. And what I did, as I mentioned, that I studied gravity theory to understand and to know more about QFTs. But that's not the only thing I did. Sometimes I also looked at the QFT side of the spectrum and try to learn a little bit about the gravity theory. And when I look at the QFT side, I'm very humble about it, because I'm only looking mostly at 0 plus one-dimensional gauge theory. I leave any serious gauge theory considerations like 3 plus 1 to Arnold, Horowitz, and other more intelligent and more capable people. I don't do higher dimensional gauge theory mostly. So I leave it to the QCD guys. But what I did is that if you look at 0 plus one-dimensional gauge theory, and we generally look at large N gauge theory, etc., I'm not going to explain what those things are here now. We can reproduce, just look at the 0 plus one-dimensional gauge theory, and look at the phases of those zero-dimensional gauge theory. And if you introduce fermion, if you introduce chemical potential for them, you actually get some part of the UCD phase diagram from very simple theories. Now, mass scales, etc., of course, do not match, but you actually get this approximate picture. You get something like, you see this tri-critical point. In one of my work, what we produce is that there, if you introduce these chemical potentials here, then what you will get a tri-critical point. and then there will be crossover on one side and exactly this kind of phase diagram on the other side between various phases. And also with Anush mainly and also with some Japanese collaborators, I also did a bit of lattice simulation. Again, I'm not generally doing anything serious in lattice. I am only looking at 0 plus one-dimensional gauge theory. These are very simple gauge theories which can model the essence of the physics, at least some part of the essence. Good. So now let me go to my second slide. So if you look at the genealogy of QFT questions, there are a few different types of questions you may ask. One are static questions, which I have discussed now that you look at, you try to understand various properties of this kind of phase diagram, etc. However, there are dynamical questions where time is involved. Although I discussed about the static questions, my main focus always were to understand these dynamical questions, and these questions involve chaos, complexity, and thermalization. Basic question, if I put it in informal language, it is that the consequence of any disturbance. If I disturb you, what happens to me? Kind of like that. What is the consequence of that disturbance? So so generally there are various kind of things you can look at there. For example, Kostas was talking about integrability. One of my work involves non-integrability of classical string motions in various kind of geometries. For example, in ADS conifold, you get a manifold. If you look at the simple string motion in a black hole background and in some other geometries, you get exactly a manifold which also arises in double pendulum. If you look at the potential picture in double pendulum, you'll get that, and correspondingly, you get this kind of chaotic picture. This is a very famous picture of chaos. This is from our paper, but this is known as Poincare section. What happens is that you can see that if you look at an integrable system, you get this nice elliptic curve in the phase space. But if you have a chaotic system, all those curves get mixed up and you get this kind of hazy picture. So this blue represents one curve, but one curve is not an ellipse. It is distributed all over the phase space. This is known as some kind of Arnold diffusion or something. To an extent, and these kind of things we have seen in those these simple string solutions, and we proved that classical string motion is non-integrable in most geometries. If you go out of some simple ADS 5, etc., you'll get anything you change, you get a non-integrable geometry. Although if you look at point particle motion in those geometries are very regular. So if you are looking at a point particle, you're basically looking at one section of this thing. And one-dimensional potential, are always integrable. But once you go look at a string motion, it is actually multidimensional. But if you just keep this radius of the string and the center of mass of the string, you get a two-dimensional manifold. And two-dimensional manifold, if you change things a little bit, you get non-integrability. So this was the kind of research. Then I also worked in thermalization, in CFT, and what happens if you do a quench in a quantum field theory. CFT is a type of quantum field theory, then what happens, etc. So these are the type of questions I looked at. Quench means sudden change in some parameters. And now there are other questions like machine learning. I'll say that it's a new branch which is not static, not dynamic. It is a new kind of things which we can do. So what am I doing in this? How much time do I have roughly?
Yes, so you have another 10 minutes. So
10 minutes.
including questions from.
Okay. So let's go into the dynamical questions that I'm looking at. One kind of model we are looking at now is called SYK model. It is a four-spin interaction and governed by a random coupling. So original SYK model had fermions, but nowadays people are looking at models where this is a random interaction between four spin in a collection of spin. The Hamiltonian is created from the interaction of four spin. So what we're looking at is that emergence of chaos in such models. We're looking at Krylov-like complexities in this model, and looking at, this famous Maldacena work where from the 4-point function or the commutator, you can learn about chaos. We're looking at this kind of thing, especially in a variation of in model where these spins are not SU2 matrices, but it is a higher SOD and SUD matrices. And then you can change for the SUD matrices, the interesting thing is that not shown by us. Recently, there is a paper by Hanada, and collaborators, I think Javeki, etc. also, where even 2 matrices are enough to give you a chaotic system. So we are looking at those properties, whether we can differentiate between this 2-point chaos and 4-point chaos. It seems that in case of the 2-point chaos, it's more like a spin glass. And for the 4-point chaos, what happens interestingly, 4-point functions give you a hint that give you a hint why a SOIK model is so famous, that you kind of get back some kind of ADS-like space, which a SOIK model is type of a field theory, and you can solve it exactly and see signatures of a gravity or string theory emerging. So we are trying to understand those kind of things in more detail. Good. Great. Then another type of questions we are looking at is called arithmetic chaos. You know that Sinai billiard, if you leave a billiard in a strange board or something, you get chaotic spectrum. You can solve these kind of things exactly in the case of the hyperbolic plane. You can look at some kind of fundamental region in hyperbolic plane and solve your equations of motion exactly to get chaos out of it. This is known as arithmetic chaos. And the solutions in this kind of things are related to modular form. They are called Bianchi mass form, and many things about them is not known. Like, there is a Langland correspondence and Weyl's proof of Fermat's last theorem, which has a conjecture which prove correspondence between modular form and elliptic curve or something. Here we do not yet know what is the correspondence elliptic curve corresponding to that. So people do various things, match a spectrum on higher manifolds and try to match with these kind of modular forms here, which is known as Bianchi mass form. So these are kind of things we are looking at. Good. So when it comes to static questions, so again, the question I'm looking at is a little bit of condensed matter thing. So this I'm looking at with condensed matter people. So if you take spin model in 2 dimensions, how we can get a continuum picture. For a lattice, these models are easily solvable. But what happens if you have some other fractal, like Serpin's cascade and those kind of things? Do you still get a nice continuum, or you get an essential singularity? So there are works which shows that something strange happens for these kind of geometries. So that is another thing I'm trying to understand. Lastly, in machine learning, from here, nowadays what people are trying is that various spin system, they're trying to simulate the ground state of the spin system through machine learning. The natural way to try this problem is hard to solve, it's possibly unsolvable. So why don't we try to make a wave function? So there are ways to kind of propose wave function through machine learning. It is related to various one-dimensional Monte Carlo renormalization, etc. So I'm trying to see that if we can get the ground state wave function in fractal lattices, can we learn those things, or can we minimize those wave functions through machine learning-like algorithms? And also, I'm looking at the similar work has appeared where people like again Hanada and few other collaborators look at the IKKT matrix model and try to estimate the ground state wave function through something known as density estimators. So what they do basically, they look at the cutting edge machine learning paper, they copy paste their code of density estimator and try to see if some kind of ground state wave function in physics can be estimated through this kind of density estimator. Generally, it doesn't work well, which is fine, but it may, but spin models are much simpler. Condensed matter people has better success using machine learning algorithms to learn ground state. And this is the kind of thing I'm looking at. So on the one hand. Okay, so why I don't know why I put this slide, but my experience in working, so my experience working in this problem is that nowadays what happens is that we can learn advanced mathematics very easily using ChatGPT, especially this various kind of algebra, new and not numerics, but the number theory, those kind of things could be learned at least at a superficial level very easily using AI, and one can use those things in physics quite easily, but not super easy yet. So maybe that's not the right term yet, but it would be, I think, in future. And also another thing is that coding still is moderately hard because before the AI agent comes, you have to run the code and you have to collect the data and you have to plot it. And there is no good way to automate it yet. Maybe in future there would be, and sometimes you have to copy paste, and copy pasting is the worst job in the world. And that's not, I'm saying that's people have actually found out, people who code, that takes most of their time and it is very means draining on your resources, both mental and physical. But you still have to unfortunately do that often if you're using AI. So maybe there will be AI agent or something which can automate the process, but it's still not there. So coding is still moderately hard. Physics is possibly very hard, but writing a paper would be easy with all those things, so which actually matters, I think. Because I was never interested in physics, I was always interested in writing a paper. I think everybody is who claims that they're interested in physics. Okay. But what would be interesting is that I think entry-level position would be gone, and that is a generic thing that's happening across the industries. So do we really need students, or whether they, or do they need them, or possibly not? Because if advanced mathematics becomes super easy, they can learn mathematics and other things using AI, so they don't need an advisor. So this is a concern, but it is also something I have seen that we are not, I don't need students anymore to work for me because I can at least go through moderately hard processes till now and work for myself. So that's where I end. So.
We have time for a few questions. One question for me, actually, Carl. So you mentioned of the SYK model, that you can have a two matrix model that's still chaotic, but it's not the SYK2 model, right? That's a different model. Because the SYK2 model, I think, is integrable. If I recall correctly. So what's the tutor model that they described?
Okay. So if you took, how can I go back? Not working. Okay, so if you, sorry, I can't go back for some reason. So if you take SYK2 model, then if you took an SU2 model, like sigma X, sigma Y, that sigma X, sigma Y model is not chaotic. Okay. So the reason being that one can show that if you write them in forms of fermion, they become localized or something in fermion, some such thing. Localized or not, I don't know exactly, but you can, they become, you can write them in terms of fermions and they simplify. But say if you have a SU4 matrix and you have two SU4 matrices, okay, now not SU2. So what happens is that these, depending on what SU4 matrices you choose, you may not get a very nice local, very nice solvable model in terms of fermion. And those models could be chaotic. So basic reason is that if you take sigma s and sigma y, they have a closed algebra, like sigma x, sigma is equal to sigma z, then you will come back to sigma x. If you take two generic SUD matrices, I don't think you have this kind of nice closed algebra. Depending on, means you can take an SU2 subset of that. In that case, you will get a nice algebra. But if you took two arbitrary ones, they may not be part of the same SU2 subgroup. In that case, they have a tendency to generate a bigger algebra. So that's why possibly those kind of models show chaos. That's what they have got numerically, I think, in their paper Hanada, Javeki, etc. We're trying to understand in more detail. And there is a question whether does it really happen, because measurement of chaos is sometimes tricky. So etc.
I suppose the natural question is, it might be chaotic, but it's maximally chaotic in that case.
That's another question. That I think is not the case. It's not maximally chaotic, but that's the final question to resolve.
It's not difficult.
So maybe you said, but when you look at these fractal lattices and taking the moon limit, is there some motivation from something like quantum gravity, or like why would you want to observe?
Yeah, so that's a very good question. So yes, quantum gravity could be one motivation. People talked about those kind of things, that whether there are fractal lattices that govern quantum gravity, etc. Another motivation comes from condensed matter, etc. My motivation is because nowadays they're making fractal lattices in lab. So they have made the Serpentine gasket with 11 electron or something. So that's one motivation. But my motivation is different. So the question is simply, it is a question of QFT, that how many continuum theory do you have? You know that in d is equal to 2, you have d is equal to 4, you have no fractional continuum theory is known. Means if you make these lattices bigger and bigger, do you meaningfully reach any continuum theory? I don't care what is the implication of that, quantum gravity or condensed matter, whatever. But that question is not known.
Does trivial relation scale with the fractal dimension? Is that what you're looking for?
Yeah, exactly. That's what I'm looking for. But the question is that whether it does, it's unclear whether that happens or not. So possibly it doesn't happen for Serpentine cascade. Is there any fractal for? What happens is that as these fractals have a lot of point where it is disjoint, the ground state entanglement entropy is what they call maybe ultra local or something, means that you don't get a nice area law out of these fractals. And that has an implications that E is not proportional. So naively we think that energy is proportional to k square in say 2 dimensions. So here you can say energy is proportional to k to the power whatever the fractal dimensions are. That is not what happens. If you look at very long range modes, they tend to localize in one place. So you do not get E proportional to k square, you get something else.
Again. Why is that?
I'll just keep going. Oh, sure. Just gonna put it here in your color. There you go. Is that comfortable? Sure. Thanks.
Thanks. And our last speaker for the first part of today is from NITheCS. Please go ahead.
Okay, thank you for the invitation, Isrof.
I think your screen sharing the whole screen so we can see your.
Oh,
It doesn't matter, it's up to you.
I can close this, I guess. Thank you again for the invitation, Vishnu, and the organizers. And also an apology, I've changed the title of the talk. I thought the talk was a bit too focused, and Vishnu was suggesting that we be more future focused. So I'm giving a slightly broader talk. I will mention some of the stuff that is in the abstract as I go ahead. So I'm going to basically be praising von Neumann algebras and trying to sell them to you and why you should probably be working on them. The title is inspired by this nice essay on Japanese aesthetics. This is a quote from the essay. The claim I'm making today is nowhere going to be nearly as strong as this. I just want to convince you that von Neumann algebras are useful. Okay, so let me start with a brief introduction. So the algebraic approach to quantum field theory tries to kind of axiomatize QFT, starting from some basic principles like locality. You impose microcausality, say that space-like separated operators commute. But you don't need to look at Lagrangians or path integrals. You just look at operator algebras in some local subregions of your theory. The question you're starting with is, if I'm an experimentalist, what observables I can measure locally where I am? Because as an experimentalist, I can't measure non-local operators anyway. What do these observables look like in some given state? Let's say a vacuum, a thermal state, some excited state that you like, and so on. There have been a set of axioms formulated by Haag and Kastler a long time back for general interacting quantum field theories in terms of these ideas. So you impose microcausality, you define some local operators, and then start from there. From just these minimal set of assumptions, you can build up the LSZ reduction and so on and so forth. Whatever you would usually want to do, you could do here. I'm not claiming that this is necessarily easier than just doing Feynman diagrams. The claim would be that it might be easier to look at algebraic ideas in certain contexts and in certain problems. One advantage of these kind of abstract formulations of QFT is you get model independent constraints. So for example, there's this famous theorem called the Riesz-Leadler theorem, which tells me how entanglement looks like in the vacuum of any QFT, which is Poincare invariant. I don't care if it's n equal to 4 super Yang-Mills, QCD, QED, whatever. As long as it's a QFT with Poincare invariance, the Riesz-Leadler theorem tells me how entanglement is encoded into the vacuum. It's been particularly useful to look at such information theoretic quantities, and I'll describe some of the results soon. Yeah, so for example, you can, let's assume our QFT is Poincare invariant. You look at some causal diamond of a region, and you just define all set of local operators which are bounded in this region, and that forms what is called a von Neumann algebra. This algebra has some nice properties which can let you extrapolate and derive theorems like the Riesz-Leadler theorem here. Yeah, so the main claim I want to make was made by Jonathan Source in these nice set of lectures that he gave trying to sell algebraic QFT to bootstrappers. So the main claim is not like you might think that algebraic QFT is just some formal mathematics you're doing just to prove theorems. Who cares if the path integral is well formulated or not? I can calculate stuff with it. I agree with that sentiment. The claim I'm making is that in certain contexts, it's a useful way to think about QFT. To motivate in what context it is useful, let me just quote a few recent results and the ways people have been thinking about these ideas. So this is just a list of results and some questions which probably have algebraic answers and which are harder to tackle using usual QFT methods. One result which I find really interesting and profound is the set of results that Subrat Raju and collaborators have found about how information is localized in quantum gravity. And these results also address some of the information loss paradoxes and so on. Another set of results you can talk of is how entanglement entropies look like in QFTs. We know we have UV divergences because of entanglement across small lengths. But if you look at quantum gravitational systems, you can define what are called generalized entropies, which Bekenstein did a long time back. Generalized entropies are known to be UV finite. So how do I explain the UV finiteness? Just the QFT entropy is UV divergent. I just couple it to gravity. Why does it suddenly become finite? A set of problems people have started looking at recently is to study closed universes, some asymptotically de Sitter spacetimes. There are arguments which tell us that the Hilbert space of quantum gravity in closed universes is one-dimensional. It's trivial, it's just one state. But then if a universe is a closed universe, how do I explain myself? I am a complex object. A one-dimensional Hilbert space cannot explain me. I think we might be able to make progress on these questions with algebraic methods. This is a kind of longer term thinking we are doing is to try and understand how we can lattice regularize quantum gravity itself. I don't mean you simulate a SYK model and claim because of holography you're seeing black holes. I mean literally impose diff invariance in a lattice regulated way. So let me elaborate on some of these ideas. So this first idea that Subrat, Raju, and others found is called the holography of information. So if you look at the first figure here, this is a picture of ADS3. You want to ask where the information in this Cauchy slice, which is yellow, is localized. What you can prove is all of the information in the yellow part of the slice is localized at its boundary, which is the red part. And the only thing that went into proving this is you define some algebra on the boundary here. You argue that the Hamiltonian of quantum gravity is part of the algebra. These two statements prove that all the information in the yellow part is localized in the red part. It's essentially a 4-line proof. This has been generalized to flat space. So in flat space, the statement is that all the information in the bulk is localized at the boundary of Scri plus, boundary of null infinity. The recent work by Subrat has also tried to do this in de Sitter, but I think that's a work in progress, so I didn't include the conclusions here. The second thing I wanted to mention is entanglement entropies. Like I said, we know we have UV divergences for QFT entropies. This stems from the algebraic fact that von Neumann algebras for usual quantum field theories are what are called type 3. Type 3 algebras don't have well-defined partial traces, so you cannot define reduced density matrices. And this is just a consequence of the fact that Hilbert spaces don't factorize in infinite dimensions. However, we know that if you couple QFT perturbatively to quantum gravity, the generalized entropy is finite. This stems from the fact that the algebra of QFT coupled to gravity is type 2, and this algebra has some nice properties which allow you to define a trace.
This sort of semi-classical gravity.
Yeah, exactly. So you look at QFT on, let's say, de Sitter, and then you impose the gauge constraints. So you say time is gauged, time translations are gauged. A nice result, which was reasonably recent by Pennington, Witten, and others, is to study algebras in de Sitter. So it's the same idea. You look at the static patch. So let's say gamma is the world line of some observer moving in asymptotically de Sitter space. The observer has access to this part of the spacetime, the static patch P. You look at a QFT living on the static patch, couple it perturbatively to quantum gravity. By that I mean you gauge time translations. So time translations along this observer's world lines are gauged. By imposing these gauge constraints in an algebraic way, you can explicitly show how the algebra becomes a type 2 algebra from a type 3 algebra. In fact, you can explicitly construct a density matrix for, let's say, the de Sitter vacuum in this static patch. And you can define gauge invariant operators by, let's say, imagine a local operator here. You can dress it to the observer's world line using some gravitational Wilson line, and that defines a gauge invariant operator. Like I said, you can explicitly find the density matrix. So the main point is these algebraic ideas are not just good for proofs. They give me an expression for the density matrix. I can compute rho log rho the trace, which is the von Neumann entropy. It exactly matches this expression. Related to this, there is this new set of ideas that Philip Hohn at Okinawa and collaborators are exploring, which are called quantum reference frames. So these were a set of ideas which go a long way back in the quantum information community. The question is, how do you impose constraints in quantum mechanical systems? And how do I study gauge transformations in quantum systems? And these have been applied to some similar setups where you have where you gauge part of the diffeomorphism symmetries and study. For example, here, I would like to study how, if I change my gauge and do a time translation, how the set of operators change and so on. So these ideas of quantum reference frames have helped us address this too. Oh yeah, I should mention what has been done so far by Witten and collaborators is to just gauge time translations, but the diffeomorphism group is much larger. So one would in fact actually like to study QFT in the static patch and gauge all the diff transformations. This is an ongoing program where again these ideas of quantum reference frames are being used extensively. Okay, so inspired by this paper which came out a few weeks ago by Pennington and others, giving an apologia for islands, let me give you an apologia for what are called Hagerup spaces. This is again an idea from algebraic QFT, which me and a collaborator of mine, Pratik Roy, who many of you know, are currently using. So what me and Pratik have been obsessed with is this inequality called the quantum null energy condition. So that's equation 1 here. This is an inequality which is true for general Poincare invariant QFTs. It tells you that if I know the stress tensor of the QFT at a point, it is lower bounded by some derivatives of the entanglement entropy. This is essentially a statement of what is called Landauer's principle. So Landauer made this famous proclamation many years ago that information is physical. If you want to store information or erase it, it costs energy. This is basically that statement. It tells you the energy in a QFT is lower bounded by how much information there is. So me and Pratik are studying some generalizations of this inequality. So as you see here, what appears is S, which is the entanglement entropy. There are generalizations of this using Renyi entropies, and even further generalizations using what are called F divergences and so on. So me and Pratik have been firstly trying to formally prove this using algebraic QFT methods. But like I said, algebraic QFT is not just good for proofs. These proofs are also seem to be constructive to us. So we are trying to understand how we can, from these proofs, understand what the bulk implications of the holographic duals would be. So for example, QNEC tells me that the entanglement wedges in the bulk are nested. So if I take a subregion in the boundary, look at its wedge, and then I take a larger subregion, the wedge of the larger region is larger than the wedge of the smaller region. So these are some consistency conditions you get for gravity itself from just this inequality. What goes into these proofs are what I want to advertise are called Hagerup's non-commutative LP spaces. Just don't worry about the name. These are some nice operator spaces. They are Banach spaces, so they have nice norms. You can use triangle inequalities, Cauchy-Schwarz inequalities, and so on. But crucially, they allow for the construction of some analogs of density matrices. Like I said before, you cannot define density matrices in usual QFT because Hilbert spaces do not factorize. It's an ill-defined operation. But these spaces allow you to do to have such a definition. They rely on something called the cross product algebra, which is in some sense a Fourier transform in operator space. So instead of looking at the QFT algebra, you do some Fourier transform, and the time variable is the modular time. So using these Fourier transformed algebras, you can actually define density matrices and study their properties. A thing that we are looking at is what is called Hagerup's reduction theorem. So this was a paper which Hagerup put out in 2008. Sadly, it hasn't been noticed so much in the high energy theory community. The quantum information people have been looking at these. The main point of the theorem is that it's a constructive theorem, which tells me how I can convert QFT quantities in infinite dimensional Hilbert spaces to finite dimensional matrix algebras. You might think we already know how to do this. Anush knows how to do this. I just lattice the QFT and I can lattice simulate everything. But the point is that the theorem I mentioned here relies on these constructions of these cross product algebras. And these algebras naturally arise in QFT coupled weakly to gravity. So the static patch example that I gave you where Witten showed that the algebra is nice, you can define entropies, it relies on this cross product. So these cross product algebras naturally occur in QFT weakly coupled to gravity. So then a natural question one can ask is, will this help me lattice regulate quantum gravity itself? I perturbatively coupled QFT to quantum gravity, define this cross product algebra, use Hagerup's theorem and define an analogous matrix algebra. That tells me how operators in the static patch, for example, would be approximated by matrices. Right, so these are some questions that me, Pratik, and others have been looking at, and also people working on algebraic QFT might hope to address in the future. So firstly is this kind of broad questions. This is something we've just been chewing on recently. I don't have anything more precise to add here other than the fact that this reduction theorem that I mentioned, we're using it in our proofs. But it seems to me that it is naturally applicable to the static patch example that I gave you, for example. The ideas from algebraic QFT are already telling us how we can explain the gauge invariant Hilbert space in perturbatively coupled QFT and quantum gravity in closed universes. So maybe this leads us to make progress on the question that I mentioned at the beginning, which is that the Hilbert space of quantum gravity in de Sitter is one-dimensional. How do I explain myself? Perhaps these algebras which are dressed to my world line tell me how the complexity emerges. Yeah, I also mentioned these ideas of quantum reference frames. So these are not just being used in formal quantum gravity or quantum field theory. You can also just study these in usual gauge theories. So Philip Horn and collaborators are also looking at studying these on the lattice. So they're starting with some simple lattice system. So it's like a Z2 gauge theory on a lattice, which is like the toric code if you've heard of it. So you can study these simple gauge theories on the lattice, and quantum reference frames are proving useful to understand entanglement structures there too. Yeah, I think that's all. Thank you.
Questions?
What is Agarup's reduction?
Oh yeah, sure. Yeah, the point is this theorem tells you if you have some quantity you would like to compute in QFT, let's say the relative entropy, it tells you how you can map this quantity to matrix algebras, to just take finite dimensional matrices and approximate the QFT quantity that you want to calculate. But like I said, you can just do lattice regulate QFT and do this anyway. But this helps you deal with algebras which arise in QFT coupled to gravity. So that's where I think this reduction theorem might be useful.
Does the theorem apply to fermionic as well as bosonic degrees of freedom?
Yes, yeah, it's fairly general. But in algebraic QFT, you don't usually talk of fermions on their own. You talk of bosonic objects constructed from fermions. As long as you have them, it's fine.
Yeah, so you construct them. Okay.
Yeah, so simplified topological quantum field theory context, would that be?
Do what? You mean the reduction?
Yeah.
It should apply, yeah.
Okay.
But like I guess this theorem hasn't been applied extensively at all in our field. So we've just been trying to see what we can do with it, yeah. It might apply, we haven't tried it, yeah.
Yeah, so I think two questions. So apologies if I missed it. So Hogg claimed that he proved that the interaction picture doesn't exist.
Yeah.
So axiomatic quantum field theory seemed like it was at a dead end. Has axiomatic quantum field theory progressed from there? And well, the reason why I'm asking is following up from Vishnu's question yesterday, where Vishnu said, well, maybe we shouldn't be worrying about, we should be trying to think about how to do field theory without gauge invariance, not enforcing a gauge constraint. And so can you do that within the context of what you're suggesting here?
Okay, so the Hogg's theorem is still true. The people have, I mean, the theorem is bulletproof, it's just there. But I would argue it has progressed in the main point I was making is that, let's say you want to compute a cross section for some scattering problem, I would not use algebraic methods at all. But if I want to address some problems which are, for example, how do entanglement entropies look like in the vacuum of a QFT, then these kind of ideas are better suited. And the second question was, yeah, about gauge invariance and so on. So that's one of the points I was making here. So these ideas, so for example here, what they're trying to do is look at a QFT living in this region of spacetime and gauge time translations. And you can do that in a way that Vishnu was suggesting, just purely in terms of operator algebras. So there is a way to make progress here.
Yeah, but I want to compute things that can be measured. So I do want to compute.
You can compute relative entropies.
So you're You're saying you wouldn't use operators that use techniques to compute cross sections, but
Because there are easier ways.
is it impossible?
No, it's not. I mean, it's just harder. Like you can prove the LSC reduction from operator algebras. I don't even write down a path integral or an action or whatever. I just look at nets of local algebras and I can derive.
I mean, LSC you get just from the Poincare invariants.
Sure, but everything should, I mean, yeah, the point is everything should just follow from Hug's axioms.
But LSC doesn't give me an amplitude.
Yes, but an amplitude is just a correlation function of operators, right?
Right? How do I compute that?
Using path integrals.
Okay, so then I need a propagator and then I need to
Sure.
force a gate.
Like I said at the beginning of my talk, I'm not.
No. So the question is, can I use these methods at all? And it seems like the answer is no.
To do what?
To calculate something that's measurable.
You can measure relative entropies.
Like a scattering process.
You can measure relative entropies experimentally.
Measure a cross section. Can I predict a cross section?
You cannot. I would think that would be harder to do than a Feynman expansion.
No. There's a difference between harder and impossible.
It's not impossible. I don't know how I would start from an operator algebra and tell you what the cross section of electron scattering with an electron is. But I don't think there is any fundamental mathematical restriction to calculating it. If that's what you're asking.
Yeah, thanks for being tonight for the talk. We can continue the discussion on coffee.
Sure.
We'll resume just at 11:30. People station. Yeah, I think those people have flights to catch it, like you could just do maybe. Sorry.
Fantastic. Wait, what? Oh, it's running. What were you showing me?
What MIT4 is doing.
Copy is going to begin by one from bits. Please go ahead.
Yeah. Thanks a lot. Good morning, everybody. Thanks a lot, Vishnu, for organizing this wonderful conference here. And I'm going to talk about one of the old problems in string theory. In fact, the origins of string theory, where people were trying to explain strong force using dual models. And so the new thing about it is that people are now trying to attack the same problem, but using some new techniques like bootstrap and a lot of the other computational techniques. And there are some surprises that people have found, and one of which I'll explain, and I'll talk about it more and in some future directions. So it is sort of widely expected that glue dynamics has a dual description in terms of strings. And from Stoof's work, we know that the perturbation theory in the large N looks very similar to string perturbation theory. But this, even though it's back in 1974, this has not been proved. We exactly don't know this map and duality, and this duality hasn't been explored because theoretically we are stuck with perturbation theory, and it's very hard to do this. So we do what we always do. We find a parameter in which we can do perturbation theory. So there is little hope of proving this conjecture at any finite n. So let's look at simplifying region, which is large n. And if you think about, if you look at the diagrammatic expansion, you will realize that at large n, what basically we are doing is we are not allowing string to break anymore. The Zn center symmetry is still preserved. And string cannot break. So the string interactions, the string theory itself are switched off, and string theory is free. But that doesn't mean it's trivial, because on the world sheet theory is very complicated. And the goal, as a first step to look at this conjecture, we can start looking at this free string theory, the world sheet theory of this free string at large n. Yeah, okay, so let me talk about how we can start doing this. So what I'm trying to think about is, let's say we are looking at a meson, but we are looking at length scales which are deep. We are deep inside the meson, so that the flux tube looks like a long string. And that's the simplifying setup that we are starting with. That let's assume that there is a long string sitting in your setup, and you can think about working in that sector as some spontaneously broken sector. And let's try to construct some use old effective field theory techniques to construct this theory. So what is the symmetry principle? That if you have a long string stretching in one particular direction, let's say the bulk is d-dimensional, then what happens is the bulk has Poincare symmetry, which gets broken down to transverse SOD minus 2, the symmetry, which is basically transverse rotations. And then there is world sheet diffeomorphism, which is ISO 1,1. And this, of course, theory has a natural cutoff, which has to be lambda QCD, because that's when you will think about things like string intersecting with each other and it's producing a glue ball, and the glue ball is emitted into the bulk. And this is where you have to start adding some massive modes to this theory. So this should be thought of as some effective field theory below this particular lambda QCD. So we are already in the confined region, and this is where we are trying to construct this theory. So from this principle, the sort of set of particles we have is d-2 Nabokov-Goldstone modes, and that's what it's just d-2 massless modes, which are d-2 transverse oscillations of the strings. And the theory will be constructed in something called the static gauge. Okay, so what we have world sheet diffeomorphism, and we can try to look at it geometrically. So geometrically, we know that the induced metric of the world sheet string itself is a geometric invariant, and also the extrinsic curvature of the world sheet, right? And then try to construct an action writing these, using these terms. And what I can do is I can rewrite this action in terms of the x's are the Nabokov-Goldstone modes, the transverse oscillations of the string. And the expansion sort of looks like this. The reason I'm giving you expressions here is that it has been proved that no matter what UV theory you're working with, as long as that theory has a string-like excitation, the first three terms are exactly fixed to these numbers. So these numbers you cannot change. So this is a very universal, this phenomenon is generally called a low energy universality in these theories, that it doesn't matter. And what is happening is, if you look at it from these perspectives, this term is a total derivative, so it doesn't contribute, and this term can be removed by equation of motion of the lower order terms. And because and then the actual corrections start from k to the power 4, and k to the power 4 has two different contractions, and these two contractions are labeled by two Wilson coefficients. Okay, so these Wilson coefficients is where the data of the UV theory kicks in for the first time. Before this, the theory is completely universal. Okay, and this theory, this effective field theory, is what we are sort of, what people in the literature are calling the world sheet theory of the QCD strings. And you could think about using this as a first stepping stone to build the complete theory, maybe at finite end or something like that. So this is what I was talking about, the low energy universality, and this is an old project because this first and we are not working in fundamental strings, so these strings have thickness, and that thickness is exactly what the string length scale is, or also the tension. So this first term in the ground state energy expansion. So what we are doing is we are putting this string on a circle of length L and doing the ground state expansion in L. So the first term actually just gives you the string length, and this has been, people have simulated this on lattice and extracted these things. This is what is called as Lucier term, which actually is also Casimir energy. Then there were further terms described in 2004, and then in 2012, 13, Aharoni and Komargatsky, and from then the subject has picked up again slowly, where people showed that until L to the power 5 terms, all of these are universal terms. You cannot do anything. I mean, there is no UV information in these terms. And the first non-universal term kicks at L to the power 7. And that exactly captures these two Wilson coefficients that I was showing you in the action here. Okay. So the project, I mean, so what people are trying to think about is in different theories, they're trying to compute alpha 3 and beta 3. And we would be interested in what this is in QCD, actually. So okay. So one thing that people are trying to attack this problem from the new perspective is that what you can do is you can think about a bootstrap program for two-dimensional flux tube theories. So these are two-dimensional theories whose particle content is d-2 Nabokov-Goldstone bosons. You write down a numerical approximation for its S matrix, impose the non-perturbative unitarity on the S matrix, and ask the program to find the allowed region for the theories, like all possible consistent S matrices that you can do. It's similar to conformal bootstrap, but here we are looking at S matrices. So what happens for d = 4, if you look into the region of alpha 3 and beta 3, the S matrix bootstrap carves out a particular region for you. So it says that alpha and beta cannot exist outside these regions. These are non-allowed theories, and only allowed theories sit inside here. And what you see, so for example, if this theory was integrable, then you would expect that the boundaries are specifically integrable. But what generally happens is you have particle production, so boundaries are close to being integrable rather than exactly integrable. And the way you do it is you construct, you do the bootstrap optimization, then you can construct numerically the S matrix, and then you can find the zeros of S matrix and look at the S matrix at a particular, plot the S matrix as a function of these parameters, and then you see these resonances. So these resonances is what I have labeled here. So one branch of this boundary has a very prominent axion resonance. Another branch is the dilaton branch. Dilaton worldsheet theories are something that is very commonly known to string theorists. We have been working with this, but because there is some sense of there is hope that, like, with these things, if you add an axion onto these theories, you might get something like integrable theory. So what people try to do is just try to find an integrable theory in the space of flux tube theories. And what they've shown is that if you just take the first three terms without these two, without the without UV the coefficients that depend on UV theory, and add an axion to it. Axion is a pseudo, it's a parity non-invariant particle. And you add it and you couple it to the worldsheet modes. And what you can show is there's a particular value of Q, this coupling constant. And if you set mass to 0, this theory becomes integrable. So there is, in the space of these theories, there is an integrable theory that we already know. And this was found out. And these simulations of SU3 and SU5 theories were done on lattice. And from lattice, what was surprising is in the exact QCD theory, meaning SU3, they found this particle. This particle actually, this axionic particle actually exists on the worldsheet theory. And it was extracted, the mass and the charge of this particle was extracted. So it's not, well, it's not integrable because it's a massive particle. Had it been massless, there was some chance of it being integrable. But anyway, there is some charge. And what this is the same bootstrap boundary that I have shown. And if you look at the boundary and plot the charges of the particle on the boundary, what you see is it comes and it settles down on a particular value of the charge. And it seems like mass is going to 0. And this particular circle here is SU3 theory. So SU3 theory has a massive axion, but its charge is exactly close to being integrable. So there are three evidences here. The one is the charge of the integrable theory, the charge that is extracted from lattice, and the charge that is coming from bootstrap, which is this horizontal line. All of them agree with each other with 10% accuracy, right? So this is an extreme. This is what is known as triple coincidence in the literature, and this is extremely surprising that QCD somehow, the flux tube theory of QCD somehow is very close to being integrable, and now we can try to understand using integrability techniques what all we can actually extract from these things. So for example, we about 2 years ago tried to explain how can we explain this triple coincidence and why this is happening, and we were not able to crack the problem, but we were able to construct a particular effective field theory which lives on an asymptotic boundary here. So somewhere here, asymptotically large beta and alpha, and in that limit, we were able to sort of show that in our effective field theory, we were able to analytically derive a number for that charge, and it seems that the integrable number is this number, and that also can be analytically derived. So you just see it's the reason of closeness is sort of a coincidence because this is 26 minus d and this is 25 minus d. Okay, but now why does actual QCD sits very close to this is still a puzzle in my opinion. And what has happened is that, okay, so you just look at what is happening further. So we just tried to do bootstrap in this region where it becomes extremely difficult. What happens is it almost lands on the integrable plane, but then it slightly lifts up and then ends back again at integrable plane. And this is where we were able to construct analytically what it happens. So what happens is you can see that there is integrability here, there's integrability here, and there is a non-perturbative violation of integrability that happens in the middle. Okay, and I mean these have not been explained exactly what is happening here, but we can try to use some techniques of approximate integrability to explain these things. People have speculated that this closeness might be related to some sort of asymptotic freedom. I don't exactly understand these statements, but maybe I'll come back to it. But it is also not understood where is the worldsheet axion coming from, because all the Navier-Goldstone bosons that existed were understood through symmetry principles. Like the string was breaking some spatial symmetries, and that's how Navier-Goldstone bosons were coming. So where is axion coming from? Is it breaking of some other symmetry? Because what all modes can string have, and are there any symmetries that are being broken? Because one thing you can think about is maybe the string has thickness, and that thickness maybe has some inhomogeneity, and that gives you that breaking, the approximate breaking of that approximate symmetry gives you some sort of massive particle, like a light particle. But it's not understood as far as I know. One thing is that what we are really doing is we are in this particular what we have done is we have constructed 2D theory much below the mass of the lightest particle in the bulk. And there are some back of the envelope calculations, and there's a lot of evidence for this, that at large n, you can just completely decouple this theory from 4D theory, right? So you would generally expect that, oh, this is a 2D theory. If you try to go at high energies, at some point you have to add quarks and complete this theory in the UV to the 4-dimensional QCD. But that doesn't happen. This theory at large n just completely separates out from the 4D theory. Okay. Now, if you're trying to do 1/n perturbations, then you will try to see interactions between the 4D theory, which will have some bulk glue balls and so on. And those glue balls can interact with the theory, like particles on the worldsheet, and then you might be able to understand how but this just has not been explored. So anything above this mass scale, this theory has not been explored, basically. So in this spirit where the theory is completely separated, so let's say if you're working in this spirit, then people have suggested, like Sergei Dubovsky and Viktor Gorbenko, that they're suggesting something called an axionic string and such, where they're saying that there is nothing extra in this theory. The only particle content is d-2 Navier-Goldstone bosons and an axion, and that's all. Until you go to UV, there is nothing. But in the theory, like we can analytically see, there are other particles. Like for example, when I showed you this particular graph, there is dilaton, there is axion. So because it's an SOD-2 invariant S matrix, it has a symmetric channel, it has antisymmetric channel, and it has trace channel. Trace channel is exactly what dilaton, like if you see a resonance in the trace channel, that's a dilaton. If you see a resonance in the antisymmetric channel, that's an axion. And if you see a resonance in the symmetric channel, that's an symmetron. But all of them don't exist as a particle. Like they might be, like these resonances are not very sharp, so they cannot be called particles in some sense. All of them exist on a flux tube theory. But then why does QCD, as simulated as we know from simulations in lattice, only contains axion? This is also a puzzle. Like I mean, this has not been explained in general. And even in fact, axionic string and that says the other particles are just not there. You should forget about them. And it also sort of tries to make this particular conjecture that theory is integrable at low energies, it becomes approximately integrable at high energies, and then there is intermediate violation of integrability. This sort of, you need to understand what is the RG flow of the string scale itself in these theories. 1/n corrections, as I said, will give you bulk and worldsheet interactions. And axion might be just an artifact of the fact that we are not allowing string to break. So maybe I can, if anybody's interested, I can tell you what this is. So axion might just be a glue ball that is stuck to the string. It's just not being allowed to go into the bulk because of the separation that we have done. And but okay, this is also not, this is my speculation. Then you can try to do bootstrap and try to look at other, so the bootstrap bounds that have been achieved now are achieved from 2 to 2 S matrices, assuming that the external particles are d-2 number Goldstone bosons. But you can, now that this axionic string ansatz is suggesting that there is only d-2 bosons and there is an axion, so we should try to bootstrap this full theory where external particles are also axions. And simultaneously, we should not only bootstrap 2 to 2 S matrix, we should try to bootstrap higher n to m matrices. And recently there has been paper doing that sort of thing, achieving tighter bounds, but in d=3 theory, which is much simpler than d=4, which has two transverse oscillations. As I said, interior generically has all of these particles, but what happens to QCD? Because it's not exactly on the boundary, it's probably slightly inside. If it's slightly inside, these particles will kick in. So the only way I can think about absence of these particles is this particles becomes extremely heavy and they decouple from the theory. So maybe that's the mechanism, but it's not explored. Again, so yeah, okay, this is something, and then okay, I think answering this particular question about why the absence of other coefficients, other particles, is related to extracting bounds on higher coefficients. So I just talked about the first two coefficients, which give you this particular space, but then you can start talking about higher coefficients, and it's slightly harder to do numerically because the alpha and beta coefficients that I showed you, the way they appear in the S matrix is they appear with power laws, but the higher coefficient appear with logs, and it's very hard to bootstrap logs in general. So that is something that is desirable and has not been done. So I guess that's all I have to say about this. Thanks. Yeah. Yeah.
You showed a plot where charge is on the y-axis. So there are two questions. What's the meaning of these different colors?
These different colors are just telling you this position on the boundary. So this is the bootstrap boundary. What this graph is telling you is there is no theory that exists for alpha and beta of values which exist here. So the only allowed values of alpha and beta as an effective field theory are just here. Okay, that's what this graph is telling you. And the boundary of this region is just, I'm marking the positions are marked with colors, and those you can go to that boundary point, construct an S matrix at that boundary point because you have a numerical solution. So you numerically can construct the S matrix, numerically find the zero of that S matrix, and from that zero you can find out the width and the mass of the resonance that exists on the boundary, and that has been plotted here. So this, let's say for example, this point is this point here, somewhere here. Yeah, that's all.
Yeah, next question is the second plot. So there, the function is double valued at certain points, right?
This plot?
Yeah. So for a given mass, there are two charges possible.
Yeah, yeah.
Right? So
I mean, you could.
There are different theories, right? So.
Yeah, they're just different theories. Yeah, that's all.
He said QCD is that circular point.
This one, yeah.
But if you go up, is there another QCD?
No. It's just see, this point corresponds to this point here, right? So QCD sits somewhere here. The other point is somewhere there, and that point doesn't even have an axion. I mean, that branch has a dilatonic resonance. So it's a different theory. Like all of these points on this graph, you can think about it as different theories. Just parameters of the theories are different. Yeah.
Could you flip to your action that you started out with?
Yeah.
Isn't there an R squared term of the same order as k to the fourth?
Oh, R squared term at the order. Yeah. Seems like that, but R. Okay, I'm not sure. Does this solve this problem that R is so R term is a total derivative, but okay, R squared won't be a total derivative. Yeah, I'm exactly not sure because generally this sort of explanation is done for for the way you construct this theory is not really do this. I mean, okay, people have done it from here also, but what you say is you have a total Poincare symmetry, and then when it breaks down, there are d-2 number goldstones. But Poincare symmetry is not completely lost; it's just not linearly realized. So what you have to make sure is you have to start constructing your theory from derivatives of your goldstones, and you have to make sure that this nonlinear the whole action is nonlinearly realizes this Poincare symmetry, and that's the I think the most clearest way of constructing an effective field theory. And I think in that sense I understand these things. So maybe R square term is here, but it becomes these terms.
Let's thank Albert again.
Let me make an announcement, please.
Yes, please go ahead.
There is a message from Farah. So a shuttle has been arranged at 16:30 from in front of the building.
Thanks. Yeah, so you will notice that my title's changed a little bit. So I still plan on talking about the defects in the abstract, but focusing a little bit more on work that I'm currently working towards, and the defects are related, but I would say I know far less about them, so we'll just touch on them a bit briefly. I notice my intro slide is a bit bare. I hope that when my slides grow up, they can look a little bit more like Isabel's. I did think about putting in a cartoon, but I don't think I can top paraphrasing Yoda, so we leave it as it is. Okay, so there's sort of two flavors of things I want to talk about today. The first one being open string integrability. So that's what I'm currently working on. And the other thing would be the defect theories. So I plan to introduce what I'm working towards currently in a slightly more pedagogical manner. So we'll have a little bit of background on integrability in ADS-CFT, open strings and spin chains, and then we'll get to the heart of the matter, and then from there touch on the defects. Okay, so I guess Kostas kind of touched on some of these things in his talk. But I'll just reiterate some of these things because I think they're just important to have in the back of your mind with why we're doing some of this stuff. So integrability in and of itself is important for, or has some important consequences. You can think of it as being a hidden enhancement of the symmetries in the theory. And when you study your theory as a dynamical system, it constrains the motion so that in theory, your theory is solvable. For ADS-CFT and the planar limit, you have integrability on both sides, which means that you can perform calculations on both sides and basically check the duality. And people have done this kind of things. What becomes more interesting is seeing, can we push integrability to a region of non-integrability and see if we can still retain our ability to perform computations, and if not, what changes when we look at non-integrability. Another powerful consequence of integrability is that, as you know, in ADS-CFT, you have the strong weak coupling duality. But because we can, in principle, calculate things completely with integrability, we can perhaps probe finite couplings, which you can't normally do. Okay, right. So we have our operator correspondence in ADS-CFT, and which means we, match two different things on each side of the theory. The things I'm interested in looking at is open strings, so that's in the string theory, and these map to open spin chains in the gauge theory, which Kostas mentioned as well. So just a bit of background, if you aren't familiar with giant gravitons and open strings. If you have an open string in your string theory, your endpoints have to end on a boundary, and this boundary is your D-branes. And giant gravitons are types of D-branes. They're giant because they're extended objects in the string theory. And one nice analogy to think about them is from the dielectric effect. So if you have two oppositely charged particles, point particles connected by a spring, and you put them in an electric field, they'll feel a force due to the electric field, and they'll stretch apart, but they can only stretch some finite distance from each other because they're connected by the spring. So at equilibrium, it will just be stretched up to some maximum distance. And this is the same idea with giant gravitons. So Kostas mentioned the RR flux in his talk. So that would be like your electric field, and the spring is like the tension. Okay, so I have a little picture here. This is a simple, one of like the more simple pictures you have of an open string attached to a giant graviton. So you can think of the green line as being your graviton, and the blue is the string attached to it. Okay, in the gauge theory, this maps to a determinant-like and a trace-like operator. So gravitons in general are determinant operators, and this gets modified a little bit, which is why I say determinant-like and trace-like when you add the open string. So this is just kind of what you have on the other side. Okay, so that's the setup. We've introduced a boundary. This is your D-brane, and now we can ask, how does this affect integrability? So if we were just looking at closed strings, everything would be integrable. Now what happens when we have this, this defect in the theory? For the maximal case, so that's a giant graviton that's expanded to fill up the space, integrability persists. But for the non-maximal case, we don't necessarily still have that. So what non-maximal means is that your dipole hasn't stretched to the full amount in that toy model analogy. Okay, So the way we look at studying this is through a mechanism called Pohlmeier reduction. And what this does is it relates the string theory to Sine-Gordon theory. Okay? It says that these things are classically equivalent. And Sine-Gordon theory is an integrable theory, which it should be if we're studying strings. And the way this Pohlmeier reduction works, I'll just go through it a bit briefly because this is getting to the heart of the problem of what I'm trying to figure out. But the idea is that you can look at embedding your string action on the sphere. So that's what I've got written down here. This is necessary to work with a Pohlmeier reduction, and from your you can construct a basis for your new space out of these fields, and these things are constrained by the like the sigma model constraints. So x dot x is 1, and your Virasoro constraints. The only thing that's left is this equation here, and that defines what we call the Pohlmeier field. And this field obeys the Sine-Gordon equation. So this is how Sine-Gordon comes from the strings. And then one thing to note around this is that it doesn't talk about boundaries at all. So from here, you don't know if you're dealing with closed strings or open strings. That's some things that you add in afterwards. And that's really the issue with what I'm trying to figure out at the moment. We know how this works for closed strings, but want to understand if we can do this mapping for open strings. So if we can look at a particular open string solution and map that to a specific solution in the Sine-Gordon theory, well, then we can investigate the integrability of the Sine-Gordon theory and try and relate that back to the string. So this would be a new way of investigating integrability. Okay, and then just a little bit of background on classical integrability. Mostly what I'm trying to say with this is that Sine-Gordon is classically integrable. There are other ways to understand integrability. Other ways people usually look at, there are classical ways people look at it. The way or the method we want to use when introducing our boundary into the theory is something called the Gauss-Zama logic of conditions. So what that is if you have some integrable theory and you have a boundary, this thing basically is a method to figure out whether that boundary will preserve integrability of your theory or not. So then what we want to do is take some open string on a non-maximal giant, map that to Sine-Gordon, and check if the boundary that we have over there is integrable or not. And then we can say whether the solutions we're studying are integrable. Okay, yeah, so it sounds simple enough, but technically the question of how we can map these boundary conditions is technically difficult. I think it's quite an interesting problem because you don't need a huge amount of background in order to start thinking about the problem, but at the same time, it has been a difficult problem. So if you're interested in it, it's I don't think it's a big adoption curve to get involved. Okay, so that's that on what I'm currently working on. Something that I'm interested in working on in the future is defects of defect theories, particularly D7 brains. Historically, well, I say historically, but maybe around 2007, 2008, this was a topic that was quite popular. People were interested in integrability of these D7 brains in your string theory. And there were some field theory predictions that said, okay, certain embeddings should be integrable and certain embeddings are not. So if you embed into the S4 of your S5, you expect integrability, but on the S2 cross S2 not, which kind of makes sense because it's slightly, it has less symmetry than the other case. And so people have looked into this and tried to confirm this on the string theory side. And the method that you'd use to try and check, so now you're not checking for integrability, but you're checking for non-integrability. So it's a slightly different approach. And there are analytic methods for doing this. And Costas and his master's student Devani have looked at this in the past, but they didn't get something to conclusively suggest that we don't have integrability in the S2 cross S2 case. So I think that's something that would be nice to show once and for all. Yep, I think that's all I wanted to say there. And then in thinking about this, recently there has been some new work being done also with the D7 brains, but in a slightly different setting. So I mentioned something called codimension. The case that I mentioned was codimension 1, which meant the other directions of your D7 brain are embedded in the ADS4. Codimension 2 defects would be in the ADS3. And these haven't been studied as much, but now this is what's gained popularity at the moment. So it's still a similar kind of problem in trying to figure out whether we have integrability or not, and in the context of holography. But it is slightly different to the other case, and it would be a cool time to get involved in it, just because it's just something that's picking up at the moment. I think actually, we can end it there. I won't go into more detail on that.
Time for some questions. So I suppose I have a question on the first part that you had, Anna. So you're still thinking of giant gravitons, open strings attached to them.
Yes.
What's the kind of computations that you're thinking of doing with them, like S matrices or?
Oh, so I'm not really thinking about working in the field theory side. So there are some predictions for the integrability already from that side. Mm-hmm. So from our side, purely just seeing if we can write out these solutions in general and then map them to the sign coordinate and say something about the integrability.
Okay, so